staff scientists, then research scientists, and leading scientists there. In the year of 2010, the Department of Agronomy at Iowa State offered him a professor there. And he accepted the position. That's what he's working now. His research interest is biochar as a soil amendment, then look at the soil quality, nutrients, leaching, and also carbon sequestration. He has been get a lot of awards from several societies, and is a fellow of the Soil Science Society of America, also Agronomy Society. And he's interested in this biochar. Then other research interests including like interaction of organic contaminants, pesticides with soil minerals, some soil surface, soil humic substance, and so on. On this project, we have some collaborations with Dr. Laird, Brian Kevin, and Steve Boyd, and we have several projects working together. Dr. Laird published about over 100 papers and also book chapters, so which heavily cited. So according to Google Scholar, it's cited over 7,000 times, and H-index about 42. Then, well, today we will share the vision of Dr. Laird to look at the carbon and carbon sequestration and carbon storage. So I will turn into time to Laird and see what his vision. So welcome him here.
Well, thank you, Dr. Lee, and it's a pleasure to be here. I want to thank Michigan State University and my colleagues. As Boy said, had a long collaboration with the chemistry group here at Michigan State University, and it's been a pleasure and an honor to be back here for today. Now, this morning, I'm going to be speaking really at a 30,000-foot level about what biochar is and what its potential role is in our economy and in addressing climate change type issues. This afternoon at 4 o'clock, there will be a seminar in the department. At what building?
Plant Soil Science Building.
Plant and Soil Science Building at 4 o'clock, in which I'm actually going to get into the science and some of the research that we've done and try to tie it together. So it's really two very different seminar presentations. Now this is entitled the Pyrolysis Biochar Platform on the Road to Carbon Negative Energy. And when I say carbon negative energy, I'm referring to systems in which, as an inherent part of that process, carbon dioxide from the atmosphere is captured, reduced, and in some way or another sequestered either in the pedosphere or the geosphere. Now, anyone who knows any thermodynamics will say that this is an uphill process. It takes energy to drive this reaction forward. So this is not possible unless we have some kind of a renewable energy system driving it in. Now, the concept of carbon negative energy means that as a side product of this process, we are deriving energy, could be electricity, heat, steam, power, something that is fueling our economy to help pay for the process. Otherwise, it's simply a waste disposal, waste cleanup process. But it's inherently inefficient because you have to partition some of the energy into the sequestration component. I'll start very briefly mentioning climate change. And I do so, I borrowed this from Dr. Hansen, and I do so for a couple reasons. Just as I said a moment ago, carbon sequestration, carbon negative energy is inherently inefficient. And the only real justification for doing that is that we have a problem in terms of climate change and we have to address it. Now this figure illustrates two key things. This is the units here are the change in climate forcing, and it's expressed in units of watts per meter squared per year. A couple of key things to note. See the red, these are the chlorofluorocarbons, which are very strong greenhouse gases. And as a consequence of the Montreal Protocols, you'll note that in the 1990s, the intensity of change coming from these compounds has dramatically diminished. Secondly, the blue is for methane, and you'll also notice that there was a rather dramatic drop in the methane signature, also in the 1990s, and this is a consequence of legislation and regulation that required the oil companies simply to flare off their methane, their unmarketable natural gas, as opposed to simply venting it into the atmosphere. Now, the point of this is twofold. Basically that through regulation and through action, government action, policy, it is possible to significantly impact climate change, or the forcing of climate change. It's already been done. The second point, however, is that carbon dioxide, the light, is the dominant player now, and we haven't addressed that yet, and we need to find a way of addressing that as we move forward. Now, in 2014, the IPCC issued the following statement related to what's known as BECCS, or bioenergy carbon dioxide capture and storage. And basically, they said that various scenarios for mitigating climate change that would keep the atmospheric concentration below 450 parts per million, which is necessary to reach the target of keeping climate warming below 2.3 C, generally require, or generally assume, that we are going to overshoot that mark because of the momentum of our economy, but require that in the latter part of this century that we actually go carbon negative. We enter a cycle in which we are on net removing carbon from the atmosphere. And to do so, they said that we need to have widespread deployment of BECCS systems and afforestation processes. And this is the only way, in the current scenario, that we're going to approach keep climate change under 2 degrees C. So what are BECCS systems? Fundamentally, there's a number of different scenarios that are out there, but they all involve some kind of a burning of biomass to generate heat, steam power to fuel the economy, coupled with the capturing of the carbon dioxide that's being emitted, and either the sequestration of that carbon dioxide in geological strata, gas wells, deep aquifers, saline aquifers, or pumping it into coal fields, possible secondary methane recovery, or several scenarios in which the carbon dioxide is recycled through biological systems, either algae, trees, or herbaceous biomass production systems. In all of these cases, however, there is a cost that is associated with the capture and storage and transport of that CO2. And this can be illustrated by looking at the data here from Gibbons et al. And this was for gas-fired power plant and coal-fired power plant. What is the cost of that energy, of that CO2 capture? And it impacts both thermal efficiency, it impacts the capital costs rather dramatically, it impacts the cost of the electricity. And associated with it, therefore, there is a significant cost per ton of CO2 that is captured. So in all of these scenarios, we're talking about a drag on the economy. Now, the pyrolysis biochar platform is somewhat unique in this sphere, in that there is the potential or the opportunity to actually capture some economic value from the process of sequestering carbon. So this is the scenario that we actually first started presenting in 2005 and published in 2008. This is a scenario for the United States, and it's based on the so-called billion-ton study with the assumption we could sustainably harvest 1.3 billion tons of biomass a year, and then the math was how we could distribute that carbon and energy through the economy. The vision being that photosynthesis was the process by which that carbon dioxide is captured. The biomass is then transported to a local pyrolyzer, relatively small scale, distributed system of pyrolyzers where it is processed, producing a synthesis gas, which is used primarily to run the pyrolysis system, so it's making its own energy, a bio oil, which is then shipped to a refinery and processed into transportation fuels and other co-products, and a biochar co-product, which is then used as a soil amendment. And when we look at the math on this, we estimate that this system could basically displace about 1.9 billion barrels of oil per year, representing about 10% of the CO2 emissions in the United States, and replacing about 25% of the oil. Now, this is not fossil fuel, this is just oil. So 1.3 billion tons of biomass is a lot, but the key point here is that even if we start taking more than 1.3 billion tons, we're going to start degrading our environment. We're going to have degrading soils, we're going to have erosion and other problems. So this is about the limit of sustainability. And so the key point here is that while this is a lot, it is nowhere near going to solve the problem. It is just a piece of the solution in this type of scenario. So what is pyrolysis? Pyrolysis, you may have heard of cellulosic ethanol, the production of ethanol through enzymatic hydrolysis and fermentation of cellulosic biomass, producing ethanol. That's one of the biochemical pathways for producing energy products. The thermochemical platform, which includes pyrolysis, gasification, and actually a whole family of different thermochemical technologies, in the very simplest sense, involves the heating of biomass in the absence of oxygen or in a low oxygen environment. And under these conditions, that biomass is thermally decomposed into a gas, a liquid, and a solid co-products. The gas is a mixture of hydrogen, carbon monoxide, methane, there's some CO2, water vapor, there's some low molecular weight organic compounds like methane in there as well. In general, though, it has an energy density of only about 1/10 that of natural gas. But it is still a combustible gas, and it can be used to generate the heat energy needed to run the pyrolysis process. Often it's not enough, but it could be optimized to be enough. The bio oil, it has about half the energy density of crude oil. It is not necessarily the best raw material to work with. It's acidic, there's some water in there, but there are ways, and I'll mention later on, of fractionating the bio oil to produce higher value products, hydrogenation to get rid of the oxygen containing functional groups in the bio oil. And so it can be refined and used for fuel and lots of different products. And the char, of course, our vision is that this would be used as a soil amendment. Key point here is that biochar is not a foreign concept going into the soil. Throughout North America, we have, since the last glaciation, some 10,000 plus years of annual or biannual prairie fires. through, we had a production of some fraction of that biomass was turned into char. This was a fire that actually I lit this spring. It's kind of interesting. And if you look back here, you can see the giant rabbit coming out of the flames. I don't know what the true story there was. Here you see the char at the margin of the burn, and that char is incorporated in the soil. When we've estimated the pyrogenic carbon or the char carbon content of a typical Iowa soil, ranges probably from about 5 to as much as 50% of the carbon. Depends on how you do it and where you take the sample, but it's a significant, a substantial amount of the carbon that is naturally in our soils. Why is it of value for a carbon sequestration perspective? Well, here's a study, a 500-day, and we just noticed that we've increased the carbon content of these soils by 69%. The key point is that char carbon is recalcitrant. So if you look at the lower graph, the green line shows a scenario in which we take, say, crop residue or leaves or whatever kind of biomass and either leave it on the soil surface or incorporate it into the soil. The half-life of the carbon in that biomass is measured in months, maybe 3 to 9 months, something like that. The point being that in a few years, virtually all of that carbon has been re-emitted to the atmosphere through microbial degradation, respiration processes, and is recycled to the atmosphere. However, when we pyrolyze that same biomass, we follow the black line here, that is during the pyrolysis process, a fraction of the carbon is returned to the atmosphere immediately as CO2 or by the combustion of the fossil fuel co-product and eventually ends up back in the atmosphere. But some fraction of it is transformed into char, which is condensed aromatic carbon dominantly and is highly recalcitrant to microbial degradation and has a half-life in the soil that can vary anywhere from a few decades to tens of millennia. And it is that difference in the half-life and the recalcitrance of the carbon that allows for a significant carbon credit and makes this system carbon negative in its totality. Unfortunately, estimating or quantifying the life cycle analysis of a pyrolysis biochar system to quantify the carbon negative, how much carbon is sequestered, is not a simple process. There are many different factors that become involved. And some of these result in actually an increase in greenhouse gas emissions. The bulk of the processes that are outlined here result in reductions in greenhouse gas. Some of these can be conflicting. So for example, there has been concern that competition between food and biomass for biofuel production could lead to a food-fuel conflict, indirect land use, which could result in potential increase in carbon dioxide emissions if, for example, we started harvesting the rainforest and used that to make char. Conversely, there is also a possibility that by putting char into soil, we could increase biomass production and the net amount of carbon coming out of the atmosphere through photosynthesis. So it depends on how it is implemented, what kind of regulation, what kind of control there is on the industry and how it is set up. Obviously, the carbon that is in the char is a fairly easy piece to quantify. You can pretty much weigh it. You can determine how much labile carbon is in there, how much recalcitrant carbon, and get a pretty accurate number on the amount of carbon that's sequestered that way. But it's all these other environmental and economic impacts that have that make it complicated and make it really context dependent to try and get an LCA, a life cycle assessment of the true impact. this is a global, this is a gas. This is 6.2 gigatons is returned to the atmosphere through the decomposition of organic materials. A small fraction of that is combusted through natural or anthropogenic. A few years ago, we thought that we were on the road to making this actually happen. We saw it economically viable, and then, of course, the price of oil plummeted down to $40 a barrel, and it was a complete game changer. The economics do not work today, not unless you have a price on carbon. This is the simple economic reality that we have to face. And so for the rest of the talk, I'm going to be looking at scenarios, systems, possibilities for making biochar systems economically viable in today's environment. Now, if and when the political system chooses to put a price on carbon, a tax on carbon, or carbon credits, or whatever policy we decide to move forward with, that will be a game changer for the system. And I think the pyrolysis biochar platform will be one of the first processes that could be adopted, because it has multiple synergistic opportunities, a way of improving soil quality, a way of enhancing crop production. So it's not just a waste disposal process. You're deriving value from the sequestration of carbon. But until then, we're left with a scenario where we have to look at niche markets and opportunities where the char may be economically viable. The first scenario I'm going to give you is here in the Midwest, where we have the emergence of cellulosic ethanol. This is a 25 million gallon per year cellulosic ethanol plant in Nevada, Iowa, which is scheduled to open in next month, in November. There's already a Poet plant in northern Iowa, and there's Abengoa down in Kansas. So we are now finally seeing the emergence of the cellulosic ethanol. And so this is a site very common now near Ames. This is biomass, corn stover, that's been harvested for the DuPont cellulosic ethanol plant. I'm a soil scientist by training, by avocation, and when I look at this photograph, I don't see this biomass. I see the soil out in front, and I ask myself, if we're taking all this residue off, what's going to be the impact on the soil? And so in 2013, we published this study, in which we had 19 years of residue removal, or not removal, with 3 tillage systems. So this was a mixed corn and soybean system. It wasn't a crop rotation. It's more complicated than that. You have to go to the paper to see the actual cropping systems there. But basically, we had either residue removal or no removal. And then there were 2 controls here. We had continuous sod and strips that had been kept in fallow through chemical treatment. And what you're seeing here is just the difference in percent organic carbon, and then the change, the difference between these 2. The stars give us some indication of statistical significance of these differences. The point here being that as a legacy of 19 years of residue removal in the cropping systems, we removed about 7.8 megagrams of metric tons of carbon per hectare. In the grass versus fallow, it was a much larger scenario, much more carbon. So it tells us that if we wait long enough, we can have a big impact on carbon storage in those soils. Not only did we remove soil organic matter, there was associated with this a loss of cation exchange capacity. Now, CEC is a measure of the soil's ability to hold cationic nutrients like potassium, ammonium, calcium, magnesium, and so on. And what we saw here on average was a loss of around 7% of that cationic exchange capacity. We measured multiple other parameters. The last one I'm going to show you is called nitrogen mineralization potential. And this is crucial from an agronomic, agricultural perspective, because you put on nitrogen fertilizer, but a lot of that nitrogen fertilizer is not actually used that year. Some of it is lost to various processes, through volatilization or denitrification or through leaching processes. Some of it, however, is stored in the soil organic matter. And that soil organic matter acts as kind of a reservoir for holding nitrogen. And it can be released back to a growing crop by microorganisms through a process known as mineralization. And this measure of nitrogen mineralization potential is a rough measure of the ability of that soil to supply nitrogen to the growing crop. And based on this analysis, we estimated that the farmer would have to put on an additional 56 kilograms per hectare, or about 50 pounds per acre of additional nitrogen to have a roughly equivalent supply of nitrogen for a crop. And farmers hear that, and suddenly the light bulb goes on, because that's money. That's a big piece of the cost of agricultural production. And so it's not just a warm and fuzzy feeling that my soil is getting better or worse. It's actual economic value associated with the degradation of the soil due to long-term residue harvesting. Now, this is an extreme case where we've been removing roughly 90% of the residue for 19 years. If we removed only 50% of the residue, a lesser amount, the impact would certainly be less, but it would be in the same general direction. In 2007, Wally Wilhelm and colleagues did a study saying, well, what does it take, as this was as the cellulosic bioenergy industry was beginning to emerge. They said, if I want to protect my soil from wind or water erosion, how much residue in tons per acre do I need to leave on the surface to protect it from erosion? They also said, okay, how much residue do I need to leave if I'm trying to protect that soil, to maintain the soil quality?